To the third lecture on chapter 10. This is covering more about valence bond theory. It's kind of picking up where we left off in the last lecture. And we are now going to talk about two different types of bonds that can be formed. So there are sigma bonds and pi bonds, and we're going to learn how to distinguish between them and what that really means. So sigma bonds are, shown by the Greek letter sigma there, and they exist in the region directly between two bonded atoms. And I think for the most part, this is what we think of when we think of a bond. We think of the electrons being, between those two atoms. So that's what a sigma bond is. Pi bonds are different. They exist in the region above and below a line drawn between the two bonded atoms. And so I have some pictures that can show you. But a single bond will have a sigma bond. A double bond will have a sigma bond and a pi bond. And then a triple bond will have a sigma bond and two pi bonds. So we always have a sigma bond. That's what's formed first. The electrons are being shared, in that overlap between the two atoms. And so that's a sigma bond. After we form that sigma bond, any additional bonds that form will be formed as pi bonds. They'll be formed in the regions above and below the plane, or kind of coming, going into and out of the plane. So we'll see what that looks like. So this is ethane, right? This is a single bonded molecule. And there is just one bond that's being formed between those two carbon atoms. And so that is a sigma bond. And so here's what it looks like. That sigma bond, again, between the two carbons is formed by the overlap of those two sp3 orbitals, right? Both of these carbons have 4 areas of electron density around them, right? They both have 4 bonds going to them, so they are both sp3 hybridized. And when we get the overlap of those sp3 hybrid orbitals, then we are seeing a sigma bond, okay? So that's, like I said, that's a single bond. That's the region directly between those two atoms. And we also are forming sigma bonds between the overlap of the sp3 hybrid orbitals and those hydrogens, right? Because again, all of those hydrogens were also single bonded. If we look at the structure down here, right? The carbon-carbon is a single bond, and all of those carbon hydrogens are double bonds. So those are all forming sigma bonds. They're all forming, in that overlap, that region directly between those two bonded atoms. Okay. And then again, we've talked a little bit about electrostatic potential maps. If we look, it's pretty much mostly the same color. We have a relatively even distribution of electron density over all of those sigma bonds. It's a little bit blue where the hydrogens are, because they're a little less electronegative than the carbons. But in general, it's mostly all the same color. We have a pretty even distribution of the electrons. So sigma bonds, so this is showing, hydrogen. Again, it's the overlap of the orbitals, and it's going to be the space directly between those two atoms. So that's what it looks like when you overlap two 1s orbitals. If we overlap a 1s and say a 2p from fluorine, again, it's going to be the region of space directly between the two atoms. And then here's what it looks like with 2p's, right? Again, region of space directly between the two atoms. Those are sigma bonds. So sigma bonds are, right between the two atoms, and that's what is formed in a single bond. Double bonds, we start to form pi bonds, and I'm going to do my best to show you and explain in pictures what a pi bond looks like. So this is ethene, which, ethene, E-N-E, that signifies that there's a double bond. So it's 2 carbons, right? That's how we get the eth. They're double bonded. And so that's this Lewis structure on the left there. When we have a double bond, if you'll remember from, toward the beginning of the slides, a double bond is formed up of 1 sigma bond and 1 pi bond. We always form a sigma bond anytime we form a bond. And then if we have multiple bonds, those other, right, the double bond and the triple bonds, those are formed as pi bonds. So the sigma bond is still going to be formed in the region of space between the two carbon atoms. So that's what's that line that's being shown right through the middle. This is, being shown as our single bond. And the pi bond forms in the region of space above and below. Okay, so I want to be very clear here. it is forming in both of those spaces. So you see where it's got the little, like, I don't know, kidney-shaped gray regions. That is the pi bond. So one pi bond shows up above and below. So when I'm asking you to draw pi bonds, make sure you draw it in the region of space above and below the bond. Okay, it happens, in both of those places. So here's what it looks like. So if we look at this one on the left, this A, right, we have the single bond, that sigma bond is being shown in part A as the overlap of those sp2, right? And this is both of these carbons are sp2 because there are 3 areas of electron density. There are 2 carbon-hydrogen bonds and 1 carbon-carbon double bond. So it doesn't matter that carbon made 4 bonds total, it only made bonds in 3 different areas, 2 single bonds and a double bond. So this is sp2 hybridized. And so there's a single bond, or there's a sigma bond that's part of that. So this is our sigma bond here in the region of space between the 2 carbon atoms. And then the pi bond forms above and below, right? Both above and below the sigma bond. So together, right, what's shown in C is we have the sigma bond happening in the region of space directly between the 2 carbon atoms, and the pi bond happening above and below the plane for the carbon atoms. Okay, so that's how the pi bonds show up. So here's another way of showing it. Again, the sigma bond is happening in the region of space directly between the 2 carbon atoms, and the pi bond is happening above and below that sigma bond. Okay, so that would be how we draw it. Okay, you can also draw it, there we go, sigma bonds, pi bonds. So here, you can draw it as the single line, right, the sigma bond, and we've got, the 2 pi bonds above and below. And if we look at the electrostatic potential map, we're starting to see more charge separation. And that's because there are more electrons that are hanging out, in the middle, here. But you can see the pi bond happening above and below. Those electrons happening, that electron density is being shown in red. Okay. Triple bonds have 1 sigma bond and they have 2 pi bonds. Okay, so we always have, like I said, we always have that 1 sigma bond that's running through the middle here. So here's our, sigma bond in the region of space directly between the carbon atoms. And then we have 1 pi bond that's happening above and below the plane. That's one of the pi bonds. And the other one, hopefully it's kind of, hopefully you can see it. The other one is going, behind and in front of that sigma bond. So this is, again, kind of hard to show in pictures. But we have 1 pi bond happening above and below, and the other one happening going into and out of the page. So that is our triple bond. But again, whenever we have a pi bond, there's always like 2 areas. There's 2 lobes of the pi bond. So if, one lobe is above, the other one's below. If one lobe is going into the plane, the other one's coming out of the plane. Okay, so triple bonds are 1 sigma bond and 2 pi bonds. Here's another way of looking at it. So this is acetylene. This is the same one we were just looking at. This is the sigma bond in the region of space directly between the 2 carbon atoms. So we have 1 pi bond that's happening above and below, right? The blue ones. So above and below, that is one of the pi bonds, and then the yellow pi bond is happening going into and out of the page. Okay, that's the other one. So 1 sigma bond and then 2 pi bonds. And it's helpful to note the pi bonds are being formed from unhybridized p orbitals. So acetylene, I'll back it up a page. Acetylene is sp hybridized because it has 2 areas of electron density. And so when we're looking at carbon, right, carbon originally had, a 2s and 3 2p's. Like that. Okay, and so we know that since it's got 2 areas of electron density, it is sp hybridized. It's a linear molecule. And so when it's hybridized, carbon makes 2 sp, there you go, sp, and it has 2 unhybridized p orbitals. Okay, so when we put those 4 electrons in, we go 1, 2, 3, 4. Okay, because it only hybridized, whoops, you know, you can think about it hybridizing this one and this one, essentially. And so it's forming those the sigma bond from the hybridized sp orbitals. You know, one of them will go here and one of them will go in the sigma bond, but the pi bonds are being formed from the unhybridized p orbitals. Those are the ones that are going to form above and below. Okay, so this is an sp orbital, and this is an sp orbital, right? We've got 2 of them going there from the overlap. But that's, you know, 1 sp, 2 sp, and then the pi bonds are being formed from the unhybridized p orbitals. There's 1 and there's 2. And if you'll recall, p orbitals are dumbbells, right? And you'll have to just pretend like I can draw. There you go. Maybe that's a little better. But the p orbitals are dumbbells. They have 2 lobes. So like the blue is 1 unhybridized p orbital, and the yellow is another unhybridized p orbital. Same thing for the other carbon. The blue is 1 unhybridized p orbital, and the yellow is the other unhybridized p orbital. And so the way that they overlap is they overlap above and below because of the 2 lobes. And same with the yellow, they will overlap into the plane and out of the plane. Okay, but again, they have the 2 lobes because the p orbitals are shaped, you know, like dumbbells. So this is important. Sigma bonds form from hybridized s and p orbitals. Pi bonds will form from unhybridized p orbitals. Okay. So here's another way of looking at it. We have same molecule that we're looking at. So here's our sp hybrid orbitals that are forming the sigma bonds. And again, another one over here, because remember, carbon formed 2 sp orbitals. So, you know, there's one of the carbons, the other carbon. And then each of the carbon has 2 unhybridized p orbitals. So one that's going above and below the plane, the other one that's coming, you know, into and out of the plane. Okay. So overlap, p overlap. Here we go. This one's a little bit hard to see. And then when we look at the electrostatic potential map, we're starting to see a lot larger separation of charge because of that triple bond. There are tons of electrons now in this middle region. There are 6 electrons there, and it's, you know, starting to affect our electrostatic potential. All right, electron density and bond order. So as we, and these are flying in the wrong order, but that's okay. As we increase our bond order, we're getting a larger and larger separation of charge because the electron density is shifted. Rather than being spread throughout the molecule, like in ethane, we start to get it more concentrated, right? Lots of electrons hanging out around this triple bond. So as we increase the bond order, right, as we go from 1 to 2 to 3 on that bond order, we are increasing the charge separation. All right, let's do some examples. So methane, this is methane is CH4. The way it would show up would be, okay, sketch the molecule. So I've drawn it below. The next part is to identify the hybridization of the carbons. So right now you should say, okay, there are 4 areas of electron density around the carbon. That means that this is sp3 hybridized. Our next step is to identify the sigma and pi bonds. So if we're looking at this, these are all single bonds, therefore they are all sigma bonds. We're going to have a bunch of examples like this. If at any point you want to, not know the answer and try it out, just pause it before I start giving the game away. Let's try another one. Formaldehyde. Sketch the molecule. So for all of these, I've already sketched the molecule for you. But again, as soon as I click onto the slide, you can pause it and go through and identify the hybridization of the carbons, or whatever atom I ask for, and then I identify all the sigma and pi bonds. This will be really good practice for you, so I recommend that you do it. Okay, so hybridization of the carbon. So we look at the carbon, there are 3 areas of electron density around the carbon. 2 single bonds, 1 double bond for a total of 3 areas. So that means that this is sp2 hybridized because there are 3 areas of electron density. And then it says go through and identify the sigma and pi bonds. So that's a single bond, so it's a sigma bond, another single bond, and then the double bond is made up of 1 sigma bond and 1 pi bond. Okay, remember there is always a sigma bond, and then as we add multiple bonds, we add in pi bonds. Let's try another. Sketch the molecule, done. Identify the hybridization of the carbon. So we look at the carbon and we see, there are 2 areas of electron density. There's a single bond and a triple bond, 2 areas. So that means that this is sp hybridized. And then going through and identifying the sigma and pi bonds, that single bond on the left is going to have a sigma bond. And then the triple bond is, again, we always have a sigma bond. And then there are now 2 pi bonds, 1 sigma, 2 pi bonds in that triple bond. Here's another. Sketch the molecule, done. Identify the hybridization of the carbon. So if we look, that carbon in the middle has 2 areas of electron density, 1 on each side. So that means the carbon is sp hybridized. And then it says identify the sigma and pi bonds. So in each of those, right, each of those are double bonds. So we always have a sigma bond and the other one will be a pi bond. So they will each be 1 sigma, 1 pi. Here's another, ethane. Identify the hybridization of the carbons. So both of these carbons have 4 bonds going to them. There are 4 areas of electron density. That means that each of these carbons is sp3 hybridized. And then it says identify the sigma and pi bonds. There are no double bonds whatsoever in this molecule. There are no triple bonds whatsoever in this molecule. So that means that all of these bonds are sigma bonds. Here's another. So propadiene. Identify the hybridization of the carbons. So let's look at, we have 2 different types of carbons. We have the, the middle carbon, and we have the 2, edge carbons, I guess we'll call them. So the middle carbon has 2 areas of electron density. It has 1 double bond and another double bond. So the 2 areas of electron density, so that means that center carbon is going to be sp. The, the exterior carbons, the edge carbons, they each have 3 areas of electron density. They have 2 single bonds, and then they have the, the double bonds. They have 3 areas of electron density. That means those edge carbons are each going to be sp2. So the center one is sp because it has 2 areas of electron density. The edge carbons are both sp2 because they have 3 areas of electron density. And then it says go through and identify the sigma and pi bonds. So all of the single bonds, right, the ones carbon to hydrogen, those are all going to be sigma bonds. And then the double bonds are each going to be made up of 1 sigma bond and 1 pi bond. So all of those single bonds are sigma, and then both of the double bonds have 1 sigma bond and 1 pi bond. Here's another example, ethene. So we have identify the hybridization of the carbons. Each one of the carbons has 2 single bonds and 1 double bond. There are 3 areas of electron density around each one of those carbons, so they are both sp2. All of the carbon-hydrogen single bonds are going to be sigma bonds, and the double bond is going to be made up of 1 sigma bond and 1 pi bond. Here's a little bit more of a complex molecule. This is going to be our last one. So it says to identify the hybridization of the carbons, but we'll do anything. Let's see. The carbon. Let's talk about this carbon first. This carbon has 3 areas of electron density, right? It has 2 single bonds and a double bond. That means this carbon with the 3 areas of electron density is going to be sp2. This carbon has 4 areas of electron density, right? It has 4 single bonds. So if it has 4 areas of electron density, that carbon is going to be sp3. So we have sp2, sp3. Just for fun, let's do the nitrogen as well. So if we look at the nitrogen has 4 areas of electron density. It has 3 single bonds and a lone pair, right? So for a total of 4. So since that nitrogen has 4 areas of electron density, it is also sp3. And we can look at the oxygen, this alcohol oxygen. It has 4 areas of electron density. It has 2 single bonds and 2 lone pairs for a total of 4 areas of electron density. So this oxygen is also sp3. Okay, and then it says, identify all the sigma and pi bonds. So anywhere you see a single bond, that is going to be a sigma bond. The only one that's different is the double bond here on this oxygen, and that is going to be made up of 1 sigma and 1 pi bond. And that's it for today. So today's lecture was nice and short and sweet. It took into account the hybridization from last time, and we used that to talk about sigma and pi bonds. And you're going to get some practice here really soon in drawing these flower diagrams and drawing the sigma and pi bonds above and below the plane. So keep practicing drawing your Lewis structures, get really, really solid at those, get really good at recognizing, the hybrid orbitals, and we're going to put that all together very soon. As always, send me any questions you have.